Good afternoon and welcome to Hand-Wavy Chemistry. Today I want to talk to you about an element that most of us just simply take for granted, and that is oxygen. Oxygen comprises about 21% of the Earth's atmosphere and is essential for life. But it also is extremely reactive and exhibits weird behaviors in a magnetic field. When we first are taught how molecules go together and bond, we usually do a Lewis dot structure. Doing so for oxygen, we come to the conclusion that there is a double bond between the two oxygen atoms. But that's all this tells us. We can combine this structure with valence shell electron pair repulsion theory to try and predict the geometry of the molecule, but with only two atoms, it's going to have to be linear. There is nothing about this model that would explain why oxygen is reactive, or why it is attracted to a magnetic field. To further highlight the limitations of this model, if we were to draw the structure for nitrogen, it looks very similar. The only difference is there is a triple bond between the two nitrogen atoms rather than the double bond we see with oxygen. However, nitrogen is considered for the most part to be inert and is often used by chemists as an inert atmosphere during reactions. So why is it that oxygen is so reactive? Well, let's talk about how molecules actually bond. Not in the Lewis structure system where we're just trying to get to the number 8, but by thinking about orbital overlaps. When two atomic orbitals come together, they can do so in a positive way or in a negative way, depending on the phases of those orbitals. This approach to bonding is known as molecular orbital theory, and we mix orbitals together to create bonding orbitals. In the case of oxygen, each atom's valence shell contains 1 2s orbitals and 3 2p orbitals that we are able to mix together. If we mix the 2s orbitals, there can be a bonding and an antibonding. And then when we begin to mix the 2p orbitals together, depending on the orientations, we get different types of orbitals. If we think about the orbitals that are directly lined up together, they will generate a cylindrically symmetrical bonding orbital, which chemists call a sigma orbital. The p orbitals, on the other hand, which point up or in and out, those will generate non-symmetrical orbitals. Those are known as pi orbitals. And in each case, there will be bonding and anti-bonding versions of these orbitals. Next, we begin to fill the orbitals from the bottom to the top. 2 electrons will go into the bonding orbital from the 2s overlap, and 2 will go into the anti-bonding from that 2s overlap. Then, for the sigma overlap from the p orbitals, we'll put in 2 electrons. And then for the positive bonding interaction of p orbitals, we get another 2 and 2. Finally, we have 2 electrons left over to go into the pi star antibonding orbitals. Electrons are negatively charged. So once we put 1 electron in one orbital, the next electron will go into the other degenerate orbital, rather than having to pair up and be squished together with another negatively charged entity. So the final molecular orbital diagram for diatomic oxygen looks like this. And we can determine the bond order by counting up the number of bonding electrons and subtracting the number of anti-bonding electrons, and then dividing by 2. Doing so, we've got 1, 2, 3, 4, 5, 6, 7, 8 bonding electrons, and 1, 2, 3, 4 antibonding electrons. 8 minus 4 is 4. So there are 4 electrons involved in bonds. Each bond contains 2 electrons. Therefore, the bond order is 2. Molecular orbital theory also predicts a double bond between the 2 oxygens. But let's look at those 2 unpaired electrons. They're sitting there. This means molecular oxygen is paramagnetic. This is why it reacts to a magnetic field. There is an unbalanced spin, unbalanced magnetic moment to this molecule. And if you were to take liquid oxygen and expose it to a strong magnetic field, it sits between the 2 poles until it all just boils away. Speaking of liquid oxygen, this compound has its own set of hazards associated with it. Firstly, liquid oxygen is incredibly cold. It's below negative 180 degrees Celsius. So there is a cryogenic risk of, if you were to touch it, receiving a cold burn. However, this is not the largest risk posed by liquid oxygen. The oxygen concentration is about 4,000 times higher than we have in the atmosphere. So even despite its incredible coldness, it will rapidly accelerate combustion. A glowing splint placed into liquid oxygen reignites with almost explosive furiosity. Furthermore, liquid oxygen can react with a wide range of different materials. Liquid oxygen is also dense, so it tends to settle and pool in one place. There is a story of a workman who had been sent to repair a leaking pipe. When they struck the pipe, the force of the impact and the vibrations from it traveled down into the ground and detonated the sidewalk. And this is not the only time that liquid oxygen has caused an explosion. There is another report of where liquid oxygen was poured on a graveled surface, and the friction and force of someone walking across the gravel caused the asphalt beneath to detonate. Because of these risks, there are a lot of rules and regulations about the transport of liquid oxygen. Now, you might think one way to protect ourselves would be to seal it up tightly and make sure that none can escape. However, keep in mind, it's only a liquid below about negative 180 degrees Celsius. Above that temperature, it's going to want to turn into a gas. And when it does so, its volume will increase over 800-fold. The pressure will be immense, and whatever container you've put it inside is going to burst apart and fail. So instead, there needs to be adequate safe ventilation methods to prevent the rupturing of any storage vessel. Now, I mentioned that nitrogen is generally considered to be inert. And we can explain this again by looking at its molecular orbital diagram. If we were to assume the same type of orbital mixing and overlap as we had with oxygen, then as we put in our electrons, we end up with a bond order of 3, and no electrons in any of the pi star or sigma star antibonding orbitals up the top there. This isn't exactly the truth. The proper molecular orbital diagram for nitrogen looks like this, where the sigma bonding orbital is actually slightly higher in energy than the pi bonding orbitals, but it doesn't change the overall conclusion that we have a stable molecule with all of the pi electrons involved in bonding orbitals. This same approach can be used to explain why helium doesn't form compounds. If we were to take 2 helium atoms and try to bond them together, we've only got 1s orbitals to worry about, so we can generate a sigma bonding orbital and a sigma star antibonding orbital. When we put all of the electrons in, we end up with 2 electrons in a bonding orbital and 2 electrons in an antibonding orbital. So overall, the bond order is 0. So there's no benefit to these two atoms being bound together. So they just drift apart and go and do their own thing. Somewhat surprisingly, the unpaired electrons in oxygen actually slow down the rate at which it reacts with organic material. Reactions involve the overlap of orbitals. So if oxygen were to come along and offer a single unpaired electron to another molecule, it's not really going to be of much interest or value to that other molecule. So instead, oxygen tends to rely on its strong electronegativity to pull electrons to itself. An exception to this is what is known as singlet oxygen. It is the first excited state of oxygen, whereby we now have those two electrons paired up. Now when oxygen goes looking for a reaction, it can offer a pair of electrons and react much more quickly. Now I refer to that excited state of oxygen as being singlet oxygen. This isn't because there's only one oxygen atom, there are still two in the molecule, but rather because all of the electrons are paired up, and so if we were to look at its spectral lines, we would only see single lines. The ground state, which is more formally known as triplet oxygen, has two unpaired electrons, and we see threefold splitting of its spectral lines. Now the reason for this splitting? Well, that is a story for another day. I hope you have enjoyed this video, and if you have, please make sure to like, subscribe, and share it with your friends. And if there is a topic you'd like to see covered in a future video, please make sure to put it down in the comment section below. Thank you, and I hope you have a wonderful rest of your day.